I would like to discuss the following topics: Legendre transformation. This is the pure or it's a mathematical topic, but this mathematical topic is useful and necessary even to introduce what's so called the Hamiltonian. The Hamiltonian is another function that may be used to replace the Lagrangian, and hence after this I would like to introduce the Poisson bracket and the canonical transformation. So before introducing the Hamiltonian, we need to some mathematical introduction using the Legendre transformation. The viewer may be familiar with what's so-called the point transformation. For instance, given the Cartesian points or the Cartesian coordinates x and y, they can be transformed to the polar coordinates r and theta, where r is equal to square root x squared plus y squared, and theta is equal to the inverse tan of y over x. And vice versa. For instance, given r and theta, you can get x equal r cosine theta and y equal r sine theta. This is called a point transformation. Legendre transformation is not a point transformation. Okay, Legendre transformation that will be introduced shortly is not a point transformation. It's somehow different. Okay, I'm sorry for this handwriting, but Legendre transformation simply transforms a function f small of x and y into another function g, which is a function of x and z. Okay, you can observe something now that x is present in x and in g, in f and g. X is termed as a passive variable. Okay, y disappears from f. Y which is present in f disappears in g, and instead we have z. Y and z are termed as active variables. What is the relation between y and z? Z is equal to partial f by partial y. This is the definition of z and its relation with f and y. Z is equal to partial f by partial y. Finally, now it's time to explicitly list the relation or write the relation between f and g. F is equal to y multiply z minus g. This is the simplest case to introduce Legendre transformation. F is equal to yz minus g. So now this is I have explained the way from the left to the right. Given f, I will get partial f by partial y, which is z, and then I can define g to be equal to yz or y multiply partial f by partial y minus f. This will be g. G will be a function x and z. Okay. By the way, the transformation is very symmetric. I mean that you can go from left to right, as I have mentioned, or you can go from right to left. Before explaining how I can go from right to left, let us complete the symmetric properties. Z is equal to partial f by partial y, and y is equal to partial g by partial z by symmetry. Okay, f is equal to yz minus g, and g is equal to yz minus f. These are definitions and come from symmetry. Now, it may be the time to verify that g does not depend on y. Okay, someone will argue that how is g is equal to a function of x and z only, although the definition of g includes y and z and f. So to get this, let us get the total derivative of g. The total derivative of a function g is equal to the partial derivatives multiply the total derivatives. For instance, dg will be equal to partial g by partial y dy plus partial g by partial z dz plus partial g by partial x dx. Partial g by partial y simply z minus partial f by partial y. Okay, and by definition z is equal to partial f by partial y, so by definition this term is zero. The next one is partial g by partial z. Partial g by partial z is equal to only y. Okay, this for instance completes or gets you the why, the reason or the motivation or the justification for this definition. And next, partial g by partial x is equal to, we don't have here x's in the y and z, it's equal to negative f by negative partial f by partial x. That's why partial g by partial x, if you compare these two expressions, is equal to negative partial f by partial x. This is, I believe, a very important slide. You need to have a look for several minutes, try to understand everything about that. Okay, and then we can move to the next slide. To the next slide, we will be able to introduce the Hamiltonian. The Hamiltonian is simply the transformation of the Lagrangian, which is a function in Q dot and T, into the Hamiltonian. The Hamiltonian is a function in Q and T and P. Q and T here are passive because they are present in the L and H. So they are passive, Q and T. The active one is Q dot. It is replaced with P. So Z here is P. So P is equal, and F is L. So P is equal to partial L by partial Q dot. This is, P is termed as the conjugate momentum, or the P is equal to the conjugate momentum. This is its definition. Okay. If you compare this, the same, the relations with the last slide, you can simply observe that partial L by partial T is negative 2 equal to negative partial H by partial T. Why? Because Q and T are passive. If you return to the last slide, you can recall that partial G by partial X is equal to negative partial F by partial X, or the partial derivative with respect to the passive variables is equal for both the function and its transformation, however with a negative sign. That's why partial L by partial T is equal to negative partial H by partial T, and the same for partial L by partial Q and partial H by partial Q, as long as you observe that that L here plays the role of F and H here plays the role of G. So these two equations are well justified. Now for P equal partial L by partial Q dot, this is the definition. Okay, but again, if you remember, Q dot, which plays the, as we have defined there, Y was equal to partial G by partial Z. So Y, H is Q dot, and G is H, and Z is P. So Q dot is equal to partial H by partial P. Okay, I believe this is clear enough. Okay, just to assure that you are not losing the track again, we mentioned that y here was the variable that disappeared, which is Q dot equal partial H, which is H plays the role of G, partial Z, Z is equal to P. So Q dot is equal to partial H by partial P. Okay, Q dot is equal to partial H by partial P. This is one important equation. Now let us return again to this one, partial L by partial Q. We know from dynamics, from Lagrange's equation, that partial L by partial Q is equal to d by dt of partial L by partial Q dot. Partial L by partial Q dot was simply P. So simply d by dt of P dot is equal to negative partial H by partial Q. Please watch carefully this equation for Q dot in terms of the Hamiltonian and the conjugate momentum, and for P dot in terms of the partial derivative of the Hamiltonian with respect to the degree of freedom. These two equations are called Hamilton's equations. Okay, they are first order equations in terms of the degree of freedom and the generalized momentum or the conjugate momentum. Okay, why these two equations are very important? Because they form a system of 2n degrees of freedom in terms of Hamilton's equation. Instead of the Lagrangian system of for n degrees of freedom, we had n equations. For n degrees of freedom, we had n equations for the Lagrangian. However, for Hamilton, we have 2n. However, they are first order, and they could be written simply in the state space or as a dynamical system. Okay. There is some more explanation for those interested in what's so-called the dynamical system and chaos. This system is very important one that's called Lorentz equations. It's a first order system written in the state space. Please, you may go to refer to the Wikipedia lecture or the Wikipedia article. It explains how Lorentz studied these equations during his research and how Lorentz discovered or rediscovered the chaos while working to solve this system of equations numerically. This system of equation is used to predict the weather condition. Okay, he rediscovered chaos, and it seems that this chaotic behavior is commonly termed as the butterfly effect. Okay, okay. It may be useful now to describe or to explore more about the properties of the Hamiltonian. An important property of the Hamiltonian is that its total time derivative. Its total time derivative is equal to what? Let us try to get the total time derivative of the Hamiltonian. Please remember that the Hamiltonian for a 1 degree of freedom system is equal to h of q and p and t. So we'll get the total derivative again, partial h by partial q multiply q dot, plus partial h by partial p multiply p dot, plus partial h by partial t, that's all. Okay, partial h by partial t dt by dt is equal to 1. The question is why I'm writing it that partial h by partial q multiply q dot plus partial h by partial p equal p dot, because this result comes or originates from easily from Hamilton's equation. Because if you remember, for Hamilton's equation, partial h by partial q was equal to something. Partial h by partial q was equal to negative p dot, and partial h by partial p was equal to q dot. Okay. The expressions are simple. Partial h by partial p was q dot, and partial h by partial q was negative p dot, so these terms cancel out. So we get an important result, which is part dh by dt is equal to negative is equal to partial h by partial t. Partial h by partial t was equal to negative partial l by partial t because t was a passive variable. So it's a very important result because given the Lagrangian, you can inspect if the Lagrangian is an explicit function in time, hence the Hamiltonian will not be a constant. But if the Lagrangian is not an explicit function in time, the Hamiltonian will be conserved or constant with respect to time. Okay, this is very important because just using this result, just looking at the Lagrangian, you can simply conclude whether the system has a constant Hamiltonian or not. This was very important hundreds of years ago, because at that time people did not have calculators or even did not have even the sliding rule. Okay. Again, so this is the conclusion. If partial L by partial t is equal to 0, then we are having something called the constant of motion, which is the Hamiltonian. It's a conserved. This is the conserved quantity. So I am summing up everything here in this neatly written slide about the Hamiltonian, and it was equal to y multiply z. Y is q dot and z is p minus f, and this is the relation with the Lagrangian again. These are the p by definition partial L by partial q dot, and q dot by definition partial h by partial p. The symmetry of the transformation, and this is the Hamilton's equation, the first one and the second one. They are green highlighted. Okay. And finally, how dh by dt is equal to negative partial L by partial t.